Today we're going to do a little demo of using the new ray flare light optical simulation integrated into Griddler and Griddler IBC to investigate the influence of wafer thickness on the solar cell performance and IV parameters. So let's get started. First, I'm going to use Griddler to quickly define a front junction device using this quick designer. So I'm going to load a TOPCon cell. I'm going to make it M10 size, half cut, and I'm gonna make a 24% efficient cell. Now I'm gonna pull up ray flare light, and I can see that this TOPCon solar cell is being described as having this front stack, which has these silicon nitride layers, aluminum oxide layer, and an emitter. And on the rear side has silicon oxide and polysilicon capped with silicon nitride. And if I click Count Optics, then click on cell cross section, I can see the breakdown of these numbers then here in the Pro version. So this number 41.64 milliamps per centimeter squared, that's coming from a total of 42.78 absorbed current, minus about 1 milliamp of free care absorption, minus a little bit of loss because of imperfect collection. And for rear incident light, I have a corresponding breakdown as well. And if we click apply all, then these numbers will be transferred to the front panel of Griddler. Okay, so in the Pro version, I can use the command to do a series of simulations based on a varying parameter. So what I'll do is I will type find JSC VOC MPP, and I can choose select parameter to vary, and I can choose thickness. I follow this template here so I can go from 25 microns all the way, let's go to 250 microns, and I step by 25 microns, and I'll save the results in TOPCon vary thickness .txt. So when I hit enter, then Griddler will run through a series of simulations, each time varying the wafer thickness. It will update the optical simulation using ray flare to calculate the photocurrent, put that result into the JL. It will also update the recombination due to the varying thickness. As the thickness increases, there is more volume for any recombination in the bulk, so that will drop the VOC. So the net effect is that the voltage should be slowly falling with increasing thickness, while the photocurrent should be rising as there's more volume to absorb. Let's see if that's true. So we hit enter. Okay, so the simulation is done, and we see there is indeed this trend where the current goes up and the voltage drops with wafer thickness. However, the voltage drop is very moderate, so then overall the efficiency does rise as the wafer thickness all the way, surprisingly, to 250 microns. We can also see if changing the cell parameters will change this trend. For instance, we can make the surface recombination terms a lot smaller so that the recombination is really dominated by bulk recombination, and that should have a greater influence on the VOC. So for instance, we can set the J02 terms to 0. We can go to base transport, make the bulk lifetime 4 milliseconds, make the surface recombination terms 0, make the emitter terms 0. So as we vary the base thickness, this term will dramatically go down, as will the intrinsic radiative and Auger recombination, with all which happens in the bulk of the silicon wafer. So now we're much closer to the intrinsic limit of the silicon, a much more perfect solar cell in terms of passivation. So we would expect as thickness increases that the voltage would drop much more steeply. So now let's rerun the simulation. And this time we can change the file name to save to no surface recom. So this time around, we see that indeed the VOC drops very steeply to the extent that the overall efficiency peaks at about just under 100 microns, right? So that really shifts the optimum thickness of the device to thinner devices. So this is an example where Rayflare, through its rigorous angular distribution tracing, can help fill in the optical side of the wafer thickness variation, while Griddler fills in the electrical side, and when combined together, we see the net results on the device. So hopefully these are good tools for solar researchers to optimize their solar cell device designs.